Hi everyone, welcome to all of you in my PYQ series of Get Chemical Engineering. So again, this one is the second PYQ series of non-isothermal reactor design. So here I will be talking about this question that has been asked in GATE 2027 from batch reactor. So here you can see a liquid phase exothermic first order reaction is being conducted in a batch reactor under isothermal conditions. So there is a batch reactor and isothermal condition is there, means temperature is constant. So temperature is not going to change throughout the reaction. And since this is exothermic reaction, so during the reactions, the heat will be liberated. So that heat is being removed while using the cooling water around the jacket, around the reactor. So here you can see this one is the cooling jacket through which heat is being removed. So some coolant would be this is the inlet of the coolant and this one is the outlet of coolant. So this fluid is being circulated, the cold fluid is being circulated and taking out the excessive heat that is being generated during the reaction inside the reactor. And this is how the adiabatic conditions can be maintained. The cooling water flows at a very high rate through a coil immersed in the reactor. Okay, so the design is not like that. So the reactor is something like that. So this one is the reactor and there is a steam jacket. This is like that, and heat is being extracted from this. So this one is in and this one is in outlet. So the if the rate constant is given as k, and let's say if I'm assuming a reaction is getting converted to product B, and this condition is isothermal reactor condition, and delta H of reaction is negative. Obviously, this one is a isothermic reaction, and the concentration at T equals to 0 is Ca naught. Overall heat transfer coefficient of this steam coil is given is U, and obviously heat transfer area is also given, that is your A, and inlet temperature conditions. So you are supposed to calculate the TCI in this one is TCI and this one is the temperature inside the reactor, because this is maintained at this condition, isothermal condition. So just try to understand the amount of heat which is being generated, the amount of heat which is being generated during the reaction from A to B. This is exothermic reaction that will be removed by the this steam jacket. So how much amount of heat is being generated during the reaction? So that will be equals to minus delta H of R and minus RA multiplied with V, and that will be equals to how much heat extracted by the cooling jacket. So UA delta T. So that will be equals to T minus TCI. Is that clear? And what this one is the first order reaction, right? So what is minus of RA? Minus of RA is KCA. And if I know that what is Ca for the first order reaction, that is equals to, if initial concentration is given, Ca naught and e to the power minus kT. Right. So with respect to time, concentration is also changing because this is a batch reactor, and you know the kinetics of the batch reactor can be written like that. So now if I'll substitute this thing, so what is the value of minus of Ra? So minus of Ra, that can be written as K Ca naught into e to the power minus kT. Okay, so once we get to know the value of rate of reactions, now I'll substitute this value over there and I'll calculate this value of TCI. So now I can write minus delta HR minus so delta HR, and what is minus RA? That is K Ca naught e to the power minus KT into V, that is equals to UA T minus TCI. So T minus TCI, that will be equals to what? Minus delta HR K Ca naught e to the power minus KT into V and upon UA. So the value of TCI can be written as T minus delta HR K Ca naught e to the power minus KT into V divided by UA. So this one is the coil inlet temperature. This one is the coil inlet temperature. the fluid or the cool fluid which is being entered through the coil. This one is TCI, and this temperature can be calculated like that. So here you can see the coil temperature is vary with respect to time exponentially. So again, this one is the answer. So your option, I think option B will be your correct option. But again, if they want to change this kind of problem, so how they can change? So let's say if we see the graph of this particular problem, so if I want to write TCI, and if let's say with respect to time, so exponentially, what is happening? It at t equals to 0, what will happen? This part will be equals to something, some constant, and when we increase the time, what will happen? It will start decreasing this in this way, something like that. Okay, if this will be the case of for if delta hr is less than 0, is that clear? And again, it can be a case where something like that. Okay, so sorry. This one is the maximum temperature TCI, and it will go. And at t tending to infinity, what will happen? The another part will be 0, and that t will be equals to TCI. Sorry, it will start something like that. So graph, I cannot say graph type because here there are two cases, delta HR and temperature, right? Sorry, time. So if I'll increase the time, this part will decrease, and if delta HR is negative, so okay, it will start something like that. It will go like that. It will start from T, which is a constant temperature, and after that it will increase, and this one is delta HR is less than 0, something like that. Though the questions can be asked in many way, but again, you have to understand how this rate kinetics of the batch reactor as well as the energy balance can be incorporated in the same problem. So this is the case. Okay. Now moving towards the next question. This is also very important question. That has been asked in 2008 in GATE examination. So you can see the homogeneous reaction A plus B is getting converted into C. So the reaction which is occurring, reactant A plus B is getting converted into C, and this reaction is occurring in a continuously stirred tank reactor here where continuous input is coming and continuous outlet is there. So conducting adiabatic CSTR at 800 Kelvin. So the temperature of the reactor is given to you 800 Kelvin, and this reactor is adiabatic. So some way you are there will be something that will be there, and continuously the heat which is this insulator would be there to prevent any heat loss or heat addition from the reactor. Is that clear? So this one is the condition. The conversion of reactant A is equals to 0.30. The relevant specific heat capacity Cp of A is given 100 joule per mole Kelvin, and again Cp of B is also 150 joule per mole Kelvin. Cp of C, sorry, Cp of B is only 50 joule per mole Kelvin. Cp of C is 150 joule per mole Kelvin, and delta H of reaction, that is minus 100 kilojoule per mole. If the feed a mixture of A and B is available at 550, so the temperature of inlet T naught, that is equal to 550 Kelvin, and exit temperature is this one. So reactor temperature is 800. So here T exit will be also 800. Why? Because this is a continuously stirred tank reactor. The mole fraction of A in the feed, that is consistent with the above data. So what is mole fraction of A in the feed? XA in the feed, that will be equals to how much? FA naught divided by FA naught plus FB naught. Why? Because feed is a mixture of A and B. So inlet molar flow rate of A divided by inlet molar flow rate of A and B sum. So by any means, if you are able to calculate the ratio of, let's say, so here this can be written as XA feed, that is equals to 1 upon 1 plus FB naught divided by FA naught. So the thing is that you are supposed to calculate only the ratio of FB naught divided by FA naught. So if you have calculated these things, then the question is very easy for you. So when we talk about the energy balance in the continuous tank reactor, so what we can say that T, that is equals to T naught plus minus delta H of reaction, and FA naught XA divided by again FA CP of A plus FB CP of B plus FC CP of C. So now let's try to talk about this particular problem, this particular parameter. So let's say if I talk about FA CP of A plus FB CP of B plus FC and CPC, that can be written as again FA naught 1 minus XA plus into CP of A plus FB naught plus FB naught minus Y, because the second reactant is FA naught XA CP of B plus FC naught plus FA naught XA CP of C, something like that. So this is very important part. So most of the time, most of the student used to forget these things, how to explain this thing. So let's try to understand. So CP of A, there is a relation between CP of A, CP of B and CP of C. So CP of B, if I am assuming is CP, so CP of A will be 2 CP and CP of C will be 3 CP, something like that. Okay. So we can substitute these things also here in this case. So if I take these things common, so FA naught, FB naught, FA naught, FC naught something. So FC naught is 0, and here you can see FB naught is not 0 because we are supposed to calculate the FB naught also here in this problem. So FA naught is there, so I'll keep these things in FA naught form. 1 minus what is XA conversion is your 30%, so 1 minus 0.3, and CP of A, that is your 100 plus FB note is not given to you, so I'll keep these things in terms of FB note minus FA note is also not given. FA note into XA is your 0.3 multiplied with 50 plus FA note is not given to you, and XA is your 0.3 multiplied with FC is your 150. So all of these things are there now. Now I can write the term FA note, the term which contains FA note, that is your 100 sorry 0.7 into 70. The first term will be your 70, and again there is a one term, so that is a 15 minus 15, and again there is FA note, so plus 45, right, and plus 50 FB note. So if I'll correct this thing, so what is this, that is 30, so 70, so 100 FA note plus 50 FB note. Ultimately, we got this, right? So the denominator here you got is 100 FA note plus 50 FB note. So now you can see that is exit temperature of the reactor is 800. So now I can substitute these things. 800, that is equals to inlet temperature, that is 550 plus enthalpy of reaction is also given, that is minus 100 kilojoule. So that is 100 into 10 to the power 3 multiplied with FA note, and XA is 0.3 divided by this one, 100 FA naught plus 50 FB naught. Is that clear? So let's try to solve this particular thing here only. So if I'll take this thing this term this side, so this is 50 plus 200, so there is 250, that is equals to, yeah, so 100 into 10 to the power 3 multiplied with 0.3 divided by, I'll divide numerator denominator by FA naught by FB naught, so that will be equals to 100 plus 50 multiplied with FB naught by FA naught. So we are supposed to calculate FB by no, FA naught by FB naught. So let's try to solve these things. So you can get 100 plus 50, and if I'm assuming this term is, let's say, a small a, so 50a, that is equals to 100 into 10 to the power 2 multiplied with 3 divided by 250. So here you can see, so 100 that plus 50a, that is equals to 400 into 3 by 5. So 50a, that is equals to 140. So a is equals to 140 divided by 50. So that is equals to 14 divided by 5. So what is a? A is your FB naught divided by FA naught. So once we get to know these things, now we can calculate the value of XA. So FB naught by FA naught is your how much? 14 by 5. So directly I can substitute here xa at f, that is equals to 1 plus, sorry, 1 upon 1 plus fb naught by fa naught is 14 by 5. So that is 14 by 5. That will be equals to 5 by 19. So mole fraction of A integer 5 by 19. Is that clear? Okay, sorry. I have done some mistake somewhere else in the calculation. So you can correct it, I think. Uh, okay, so I'm leaving these things up to you. What is the final answer? But again, I have told you the method. This is the method, but in calculation, you can, take care of these things. Is that clear? Okay, so I'll be moving towards the next problem. This problem is also very, very important. This question has been asked in 2016 in GATE. So, see, there is a graphical questions, and you can say a liquid phase irreversible reaction is getting converted to B. A liquid phase irreversible reaction is getting converted to B is carried out in an adiabatic continuous tank reactor. So, you have a CSTR, and this reactor is operated in a adiabatic condition. The reactor reaction is elementary and follow the first order rate law. So n is equals to 1. Obviously, elementary reaction is there. For the reaction as a function of temperature T, the different values of rate of reactions minus R is denoted by number of something is given to you and graph is given to you. Is that clear? So from this particular plot, you can see that this graph has been given between X versus temperature. And what is this temperature? That is the temperature at the exit of the reactor. And the conversion, you are supposed to calculate the volume of reactor required when conversion is 80%, right? Okay, so if I want to write this design equation of CSTR, so I can write B by V naught that is equals to obviously CA naught XA upon minus RA. But rate of reaction is not given to you in this particular problem, right? I mean, first order reaction is there, but you can write minus RA KCA. But concentration at the exit condition is not given to you. But how we can calculate these things with the help of this non-isothermal condition, right? So this is a combination of isothermal and non-isothermal reactor condition. So first I'll do that temperature is given to you, that is 350 plus 25 XA. But conversion is 80%, so I can calculate exit temperature of the reactor, that is 350 plus 25 multiplied with 80 upon 100. So that is 370 Kelvin, right? So once we get to know the the exit temperature, so this one is the rate plot. So rate is here 50, 20, 10, 5, something like that. Okay. So with the help of this particular data, you can go to the graph and you can calculate the value of the rate of reaction. So let's say 370 Kelvin and a conversion is this thing. So this one is the conversion line. This one is the conversion line, and anywhere here you will see there is a 370 Kelvin. So if you will go here, this line will cut here. Okay, so the intersection point, you will see the rate of reaction is there. So this reaction is for 10. Is that clear? So from here you can see minus rate of reaction is your 10. Once you get to know the reaction, this is the part of major part of this particular problem. Now you can use this particular formula. So inlet concentration is given to you, volume, and volumetric flow rate is not given, but molar flow rate is given 100 mole per second. So V that is equals to Ca naught V naught into Xa divided by minus Ra. Ra is 10. What is volume? Volume. Ca naught V naught is Fa naught. Fa naught is given to you 100 multiplied with Xa is 0.8 divided by 10. So if you'll do these things, you will get 8. So volumetric flow rate was a mole per second. So this will be in your rate is meter cube. So 8 meter cube. So the answer from this particular problem will be 8 meter cube. Okay, so this is not very tough problem, but this was very simple. But you just have to understand what kind of data that has been given in the problem and how can we calculate the rate of reactions from the graph. So again, let's say if similar questions are not coming in the GATE examination in future, but again, this kind of problem or this kind of concepts can open your mind, to solve, various kind of problem from non-isothermal reactor condition. Is that clear? Okay, so this was another type of problem that was very, very important. And this problem There are another two problems that has been left that I'll discuss in the next lecture. So these two problems have been asked very recently in 2019 and 2022. This is very, very important problem, and we'll see in the next lecture. Okay, thank you.